Hello everyone, I'm Shuai from Fudan University. It's a great pleasure to present our work. Notice the Imposter, a study on user tag spoofing attack in mobile apps. In recent years, mobile surveys have become increasingly personalized for different users or user groups. The core technology behind this is user tag sharing. Let's take a ride-hailing service as an example to illustrate this. With these surveys, the passenger's location is used to find nearby available cars and drivers. This service helps class passengers and drivers together, ensuring that passengers located in different places can quickly find suitable rides. Here we name the passenger's location as bound tags and share the back information of nearby drivers as free tags. Then, what do bound tags and free tags mean? Essentially, they are both user tags used to describe metadata information about users in different dimensions and form the final user digital profile. For example, user tags may include the user's identity, birthday, and location. With these user tags, personalized mobile service can well understand their users and select appropriate user tags to provide personalized service. For example, in the case mentioned above, user's location tag is selected to cluster passengers and nearby drivers together. For these user tags that the personalized mobile service rely on, we call them bound tags. And for the user tags shared back by the service, they are referred to as free tags. Normally, the typical process of user tag sharing is using a user's bound tag to exchange other users' free tags. However, it raises the question of whether malicious users could potentially deceive the tag service by forging his own bound tags and thereby gaining unauthorized access to the shared free tags, namely the user tag spoofing. Well, the answer is yes, and here is an example saying how user tag spoofing works. This case is a personalized art sharing service, namely the Today service shown here. As the name suggests, this service shares artworks, including their images, authors, and galleries based on the current user's data tag. This mobile application sets the limit for non-subscribe users, allowing them to view only 5 art pieces per day. To access the entire artwork database, a subscription fee is required. However, upon our analysis, it is found that this service is vulnerable to user tag spoofing. When an attacker forges his own data tag, the service is deceived to return artworks corresponding to the crafted date. By repeatedly exploiting this vulnerability, the attacker can gain complete access to the artwork database without paying for a subscription. Currently, academic research on mobile privacy security primarily focuses on privacy collection, with less attention given to user tag spoofing, which happens in privacy sharing. There are only a few studies that specifically address user tag sharing in certain business scenarios such as contact discovery service. However, the whole picture of user tag spoofing in the real mobile world remains unknown. In order to understand the landscape and severity of user tag spoofing, while it is necessary to effectively identify the risk of user tag spoofing. However, achieving this goal is non-trivial, and there are two main challenges that need to be well addressed. First, there is a wide variety of personalized mobile services, and each has its own unique set of bound tags that depend on concrete business logics. Thus, how to develop a general and effective method to identify these bound tags on such a situation is challenging. Second, once the bound tags are identified, it is important to determine how to forge valid values for them. On the one hand, for the same type of bound tag, such as user gender, mobile service may use different value formats. For example, some services may use the number 1 to represent being male, while others may use the string male to represent the same gender. On the other hand, for fixed format bound tags, like email address, there is a vast range of valid values, and the range of valid email address in mobile service is typically unknown and may be varies across different services. Simply adopting brute force ways to test against a given service requires too many tries to succeed. To address these two challenges, our approach is based on two key insights. First, since bound tags are used to differentiate individual users or group of users from others, it means that they can describe the unique attributes of users and thus typically carry sensitive semantics. Therefore, the sensitive semantic is a reliable indicator for the existence of bound tag. Again, regarding crafting valid bound tags, we observe that apart from the service on the test, the targeted mobile app also has other services which may share back the bound tags we need. And since these bound tags come from the existing users of the targeted mobile app, they are supposed to be valid for acting as the crafted bound tags. Okay, based on these two insights, we have designed UTSFuzzer, whose principal design is divided into three phases. First, from a large number of mobile applications in the wild, UTSFuzzer needs to pick out candidate applications that have user tag sharing service and subsequently identify the employed bound tags. Second, given the identified bound tags, our tool needs to effectively explore their value space, which can empower the tag imitation and help generate forged but valid bound tags. Finally, by submitting the crafted bound tags to the service on the test, UTSFuzzer needs to determine if the test service is vulnerable according to its responses, and vulnerability reports will be generated accordingly. Okay, in the first phases, manually registering, logging, and triggering service for each individual application would introduce unacceptable manual efforts, which is infeasible. To pick out candidate applications, the core idea of the UTSFuzzer is to search for the code pattern of user tag sharing in mobile apps code. In particular, a mobile app needs to have network interfaces that send out bound tags and share back free tags. So by starting from the network API interfaces and conducting forward and backward analysis, UTSFuzzer can quickly identify whether the code pattern exists or not, so as to pick out the candidate application of interest. For the selected applications, UTSFuzzer will dynamically test them to trigger their user tag sharing service. By monitoring the network traffic and checking the sensitivity of service parameters, the employed bound tags can be effectively identified. After triggering the user tag share service and identifying the employed bound tags, we need an effective way to explore the value space of these bound tags, so as to generate fake but valid bound tag values for fuzzing. The core idea of UTSFuzzer for exploring bound tags value space is building a user tag value database with tag values shared by mobile service. Specifically, its strategy consists of three aspects: in-app imitation, cross-app imitation, and general imitation. Suppose that the service on the test relies on user email address, i.e. the bound tag, and the tester's email address is alice@gmail.com. In-app imitation will look for other user email address returned by other service in the same app, such as bob@gmail.com. These values will then act as seed to replace alice@gmail.com. Since bob@gmail.com is from the app providing the service on the test, it must belong to the app's existing users, and therefore must be valid for conducting user tag spoofing. If in-app imitation does not work, cross-app imitation will be used to increase the possibility of forging valid bound tags. Its core idea is to refer to user tag values shared by service in other apps. For example, if other apps share email address such as jet@gmail.com, this email address can also be used as seeds for crafting bound tags. Finally, if neither in-app imitation nor cross-app imitation works, UTSFuzzer will apply general imitation on string and numeric bound tags. For example, alice@gmail.com will be imitated into 4 candidate values as shown here. During imitating bound tags and generating the forged ones, in-app imitation strategy is always preferred, followed by cross-app imitation, and finally the general imitation. After the value space of bound tags is effectively explored, the value of identified bound tags will be replaced with the mutated ones, and the response of the tested service will be monitored to determine whether it is vulnerable or not. Specifically, UTSFuzzer judges whether there is a crafted bound tag that results in the sharing of non-null and different free tags. If so, then the tested service is vulnerable to user tag spoofing. Okay, based on UTSFuzzer, we conducted a large-scale experiment on over 20,000 popular real-world applications. Our goal is to reveal the full picture of user tag spoofing. To achieve this, I will have 3 research questions to answer. First, is UTSFuzzer effective? Second, how many real-world mobile services are affected? Last, what attack efforts may be introduced? Okay, for the first research question, our large-scale experiment has discovered 100 affected mobile applications with a total of 115 risky mobile services. It is worth noting that due to ethical considerations, UTSFuzzer was able to mutate each bound tag only 4 times during the actual testing. Therefore, the detection results of UTSFuzzer are non-exhaustive. To validate the reliability of UTSFuzzer, we employed a combination of random sampling and manual verification to assess the tool's performance. The validation results show that UTSFuzzer achieves outstanding performance in detecting user tag spoofing risks, with a precision rate of 95% and a recovery rate of nearly 99%. In addition to the above analysis, we look deep into the detection results of the large-scale experiment. It is revealed that 11 types of bound attacks are affected, such as email address, and sensitive user data, including but not limited to demographic information, were exposed. The accumulated installs of all affected mobile apps reached to 430 million, which demonstrates the large scale of affected users. Moreover, the existence of user text spoofing risks in iOS platform is confirmed. It is worth noting that in theory, user text sharing service could exist on various platforms such as Android, iOS, PC, web, and so on. So the actual impact of user text spoofing may be even more widespread. As well as the sensitive user data leakage caused by user text spoofing, we further reviewed a series of attack efforts that attacks may conduct. Due to the time limit, we will only introduce a case study showing the illegal monitoring of user activities. Interested audience can read our paper for more details. Okay, this case concerns a service for user group organization where users are differentiated based on their identity type and are only provided with information of groups that they have joined. In this application, users can join specified groups by using the right group passcodes, which further allows them to access various user activity information like chat history, plans of activities, and so on. However, as being vulnerable to user text spoofing, this service will leak information of the victim's groups when an attacker manipulates his own user identity tag and impersonates himself as the victim. The leaked information includes the passcodes of all groups that the victim has joined. In consequence, the attacker can easily join all of the victim's groups and access all the exposed information like plans of activities and thereby be able to conduct the illegal monitoring. In conclusion, in this paper, we first conduct a systematic analysis of user text spoofing user text sharing service. Then, according to the two key insights coming from the systematic analysis, we designed a non-fuzzing-based security rating tool for automated application of user text spoofing risks. Finally, based on this tool, we formed a large-scale security assessment to review the landscape and the severity of user text spoofing in the wild. And we have responsibly notified the affected app developers to help them fix the issues. For more details, please feel free to follow our paper. Thank you.